The design described, featuring an outside pad-mount transformer feeding two buildings with multiple tenants, is permitted under the National Electrical Code, specifically Exception 5 of Article 230.40. This exception addresses the location of load centers and panel boards, permitting service entrances located outside buildings and therefore not in hazardous classified locations. A single transformer is sufficient to supply both buildings in this scenario. Distributing the load by installing two disconnects for the building with 16 meters is acceptable. This offers the advantage of redundancy, meaning that if one disconnect fails, the other can maintain power to at least a portion of the tenant. The NEC mandates that disconnects must be located within sight of the transformer, typically interpreted as within 25 feet. Fault current calculation should be identical for both disconnects, as they are both fed from the same transformer. For design enhancement, consider installing a ground fault circuit interrupter, or GFCI, on the disconnect serving the second building. This adds an extra layer of protection against electrical shock hazards. Let's elaborate on these points. Firstly, the NEC allowance for the described service entrance configuration hinges on the service equipment being located outside, avoiding hazardous locations. Secondly, using a single transformer provides an economical solution, eliminating the need for a second transformer and associated installation costs. Thirdly, the implementation of two disconnects for the main building enhances service reliability. In the event of a failure in one disconnect, the other can continue to supply power, minimizing disruption to tenants. Fourthly, the requirement for disconnects to be within sight of the transformer ensures easy access for maintenance and emergency situations. Fifthly, the equal fault current calculation for both disconnects simplifies the overcurrent protection design, ensuring consistent protection across the system. Sixthly, the addition of a GFCI on the disconnect feeding the second building improves safety by mitigating the risk of electrical shock, particularly in areas where moisture may be present. Now, let's consider some other factors that can influence the design. The size of the transformer must be adequate to handle the total load of both buildings, including all tenant loads and common area loads. The overcurrent protection for the transformer and disconnects must be properly sized to protect the equipment from overloads and short circuits. The grounding system must be properly installed to ensure a safe and effective path for fault current. The wiring methods must comply with the NEC requirements for the specific application. Additionally, consider the future expansion needs of the office complex. It may be prudent to select a transformer with a slightly larger capacity than currently required to accommodate future growth. Also, ensure that the service entrance equipment is readily accessible for maintenance and repairs. The placement of the transformer and disconnect should be carefully considered to minimize the length of the service conductors and to avoid obstructions that could hinder access. Furthermore, it's important to coordinate the electrical design with other building systems such as the HVAC system, the fire alarm system, and the plumbing system. This coordination can help to prevent conflicts and to ensure that all systems operate safely and efficiently. Another important consideration is the voltage drop in the service conductors. The voltage drop should be kept to a minimum to ensure that tenants receive adequate voltage at their panel boards. The NEC recommends that the voltage drop should not exceed 3% for power, heating, and lighting circuits. To minimize voltage drop, it may be necessary to use larger conductors or to install the transformer closer to the buildings. In addition to the NEC requirements, there may be local codes and regulations that must be followed. It's important to check with the local authorities to ensure that the electrical design complies with all applicable requirements. Finally, it's important to have the electrical design reviewed by a qualified electrical engineer to ensure that it is safe and compliant with all applicable codes and regulations. Now, let's talk more about the ground fault circuit interrupter, or GFCI. GFCIs are designed to protect people from electrical shock by detecting small imbalances in the current flowing through a circuit. When a GFCI detects an imbalance, it quickly interrupts the circuit, preventing a dangerous electrical shock. GFCIs are particularly effective in preventing shocks from ground faults, which occur when current flows through an unintended path to ground, such as through a person's body. GFCIs are commonly required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Installing a GFCI on the disconnect that feeds the second building provides an additional layer of protection against electrical shock, particularly in areas where tenants may be using electrical equipment outdoors or in damp locations. GFCIs are relatively inexpensive and easy to install, making them a cost-effective way to improve electrical safety. Now let's explore the topic of fault current calculations in greater detail. Fault current is the amount of electrical current that flows during a short circuit. Where a short circuit occurs, the current can reach very high levels, which can damage equipment and cause fires. It is important to calculate the fault current at various points in the electrical system to ensure that the overcurrent protection devices, such as circuit breakers and fuses, are properly sized to interrupt the fault current safely. The fault current calculation depends on several factors, including the size of the transformer, the impedance of the transformer, the length and size of the conductors, and the impedance of the equipment. The fault current calculation is typically performed using a computer program or by hand using simplified formulas. The results of the fault current calculation are used to select the appropriate overcurrent protection devices. Overcurrent protection devices must be able to interrupt the fault current without being damaged. They must also be able to interrupt the fault current quickly enough to prevent damage to other equipment. The NEC provides guidelines for selecting overcurrent protection devices based on the fault current calculation. Let's now discuss some potential challenges in this type of electrical service design. Space constraints can be a significant challenge, particularly in urban areas where space is limited. The pad-mounted transformer, disconnects, and meters all require space, and it may be difficult to find a suitable location for all of this equipment. Coordination with the utility company is also essential. The utility company must approve the electrical service design and must provide the necessary equipment to connect the building to the utility grid. The utility company may have specific requirements for the location and type of equipment that is used. Another challenge can be obtaining the necessary permits and approvals from the local authorities. The electrical service design must comply with all applicable codes and regulations, and it may be necessary to obtain permits from various agencies before construction can begin. Cost is also a major consideration. The cost of the electrical service design can be significant, particularly for large office complexes. It is important to carefully consider the cost of all of the equipment and labor involved in the design and installation. Finally, ongoing maintenance is also something to plan for. The electrical service equipment must be properly maintained to ensure that it operates safely and reliably. Regular inspections and maintenance can help to prevent problems and to extend the life of the equipment. In summary, the design of an electrical service entrance for an office complex requires careful consideration of several factors, including NEC code compliance, transformer requirements, disconnect placement, fault current calculations, and safety considerations. By following best practices and working with qualified professionals, it is possible to design a safe, reliable, and cost-effective electrical service entrance that meets the needs of the office complex. In the context of improving the design, consider the implementation of smart metering. Smart meters provide real-time data on energy consumption, enabling tenants to monitor their usage and identify opportunities to save energy. Smart meters can also facilitate demand response programs where tenants are incentivized to reduce their energy consumption during peak periods. Another potential improvement is the use of energy-efficient lighting and equipment. LED lighting, for example, can significantly reduce energy consumption compared to traditional lighting technologies. Energy-efficient HVAC systems and appliances can also contribute to significant energy savings. Also think about renewable energy integration. The installation of solar panels on the roof of the office complex can provide a source of clean, renewable energy. Solar panels can reduce the building's reliance on the utility grid and can lower its carbon footprint. The design should include provisions for future expansion or upgrades. The electrical system should be designed to accommodate future increases in load as the office complex grows or as tenants install new equipment. This may involve selecting a transformer with a larger capacity or installing additional conduit and wiring. Consider the accessibility and maintainability of the electrical equipment. The transformer, disconnects, and meter should be located in a readily accessible location for maintenance and repairs. The equipment should also be designed to be easily maintained, with readily available replacement parts. Think about the aesthetics of the electrical equipment. The transformer, disconnects, and meters should be located in a visually appealing location that does not detract from the overall appearance of the office complex. Landscaping or screening can be used to hide the equipment from view. Also consider the security of the electrical equipment. The transformer, disconnects, and meter should be protected from vandalism and theft. Fencing or other security measures can be used to deter unauthorized access. Don't forget about surge protection. Installing surge protection devices at the service entrance and at individual panel boards can protect sensitive electronic equipment from damage caused by voltage surges. And lastly, power quality monitoring. Monitoring the power quality at the service entrance can help to identify potential problems such as voltage sags, voltage swells, and harmonics. Addressing these power quality issues can improve the performance and reliability of the electrical system. So, in conclusion, the design of the electrical service entrance is a critical aspect of the overall building design. By carefully considering all of the relevant factors and by following best practices, it is possible to create a safe, reliable, and efficient electrical system that meets the needs of the office complex and its tenants. Remember to prioritize safety, compliance, and long-term performance in your design decisions. Ensure that the electrical system is designed and installed by qualified professionals and that it is regularly inspected and maintained. With careful planning and execution, you can create an electrical service entrance that provides reliable power and enhances the value of the office complex.